To give a quick kind of discussion of what I've been doing all semester with special topics with Professor Schweinhart. We're doing polyforms research. So like vaguely, I've been told this has applications to chemistry and biology, and within biology specifically protein folding. And protein folding has applications to cancer research. So I'm not really familiar with why this is useful or how this is applicable, but I will take everyone's word for it because it seems like this is important and I have a lot of fun doing it, so that's kind of does it for me. But let me just show you guys kind of what I've been doing. So we're dealing with basically these shapes. They're called polyforms, and in the 2D case they're called polyominoes. And you might actually recognize some of these. So let's talk about a specific version of the polyominoes, and I'm going to keep this pretty high level, so you don't need to know the stuff, like as long as like this, we're not going to go too deep. I'm going to go pretty deep, but it's not going to require any background. So let's start with just the tetraominoes. Okay, so the tetraominoes, what's a polyomino? A polyomino is a complex of squares that is strongly connected. Let's unpack that. So complex of squares just means like a bunch of squares. So like this might be like a complex of squares, right? Just a whole bunch of squares, whatever, right? Okay, we've got squares. But this is not a polyomino. Strongly connected means it has to share a face like this. Okay, so none of these share faces. So this is not good. This is nothing. We don't care about this. But this is a polyomino, right? So this is a domino. This is, I think, a triomino, and this is a tetraomino. Okay, and let's draw another tetraomino, right? So strongly connected means they share a face. So let's make this one, right? So all of these pieces, I'm going to put dots inside of them, so it's a little bit easier to visually distinguish them later on. So this is another tetraomino. Okay, let's draw another tetraomino. This is another tetraomino. Okay, so we have 3 tetraominoes. I think we're missing one tetraomino, and that is this one. Let's draw it flat. So these are all of the tetraominoes, assuming that rotating you get the same one. So like for example, I'm not going to draw the flat piece. I'm not going to just draw this on its side. So these are all the tetraominoes, and there's arguably more if you include all the rotations and stuff. And actually, in the stuff that we're doing, we are counting rotations as different polyominoes. Now we're working on the 3D case of this that are called polyforms, but I'm going to stick to the 2D just so it's easy to visualize. So let's just think about like properties of these things, right? So they're made out of squares. They have a perimeter, right? So I'm going to draw dots around the perimeter. I'm using like a weird definition of perimeter here. These are all of the places that are like strong, that are like air that contain no piece, but are strongly connected to a piece. So I'm not going to count this little corner bit as part of the perimeter, right? So these corner bits aren't part of the perimeter. This is all part of the perimeter of this piece, right? So of the S piece, we have, this is all perimeter, okay? All of these spots. Okay, so if I were to add, one way to think about the perimeter, so if I were to take like another piece like this and I wanted to add it to one of these, I could put it anywhere where there is a dot, right? So for example, if I want to add a piece, I can't add a piece here. This is not good because this is not a polyomino. But I can add a piece anywhere where there's perimeter, so I can do this, right? I can do this, right? This is okay. All right. Let's talk about what we were actually trying to do with these things. So with these polyominoes, our goal was to randomly sample them. And initially we thought about enumerating them, just kind of listing all of them like I did for the tetraominoes. So to go back to all the tetraominoes, I just have to scribble a few of these out, but whoops, not that many of them out. But anyways, you saw the tetraominoes. The idea was that we would, we could enumerate them and then pick them at random. So one way of doing this is to kind of draw all the pieces out like this. Okay, so I'm gonna completely give up on this guy. He's kind of toast. And then do this. Okay, and now I can just pick with 1/4 probability which one we get, right? But that doesn't necessarily, that might not necessarily be the distribution we want to sample from. So Enumerating them actually takes a lot of time. Enumerating every polyomino with the algorithm we had earlier took this time complexity. If you don't know what that means, don't worry about it. It just means that like this measures how fast the size of your problem grows relative to the size of the input, or like the time it takes for you to finish the problem relative to the size of the problem. I guess one way to think about it is if I ask you to eat a hot dog, you would eat it basically in the same amount of time, right, every time. If I ask you to eat 300 hot dogs, it's not going to be as simple as multiplying the time it takes you to eat one hot dog times 300, because that's a lot of hot dogs, and eventually you're going to have to slow down and go about your day and then come back and eat more hot dogs. You can't eat all the hot dogs in one sitting. And so hot dogs are a great example of something that is not a order n problem, right? Now there's some problems that are order 1 problems. These are problems that take the same amount of time regardless of the size of the input. So for example, if I ask you to put a brick in a house, it doesn't matter how many bricks have already been placed. The act of putting a brick is going to take the same amount of time regardless of how many bricks have already been placed, right? So this is a problem that has no relation to the size of the input. It's always the same amount of time, right? This is terrible time complexity. Imagine if each this is not strictly speaking the number of operations, but if each operation takes like a millisecond, right? Just 13 to the power 13 is a huge number. 15 to the power of 15 is a massive number. Like, you're not going to be able to, you have to start worrying about the heat death of the universe. You're not going to be able to finish solving your problem in time. So this is just a quick kind of primer on growth order. And I'm going to be using this to kind of show how fast my algorithms are. And our algorithms are, because we had several different approaches by several different students. So let's talk about what we were asked to do. We were asked to randomly pick these polyforms. So the kind of the solution to this n to the n is an algorithm called Markov chain Monte Carlo, and it doesn't necessarily have a time complexity. It's also not a fair comparison, because in this one we're actually enumerating every single polyomino, but in Markov chain we're going to dynamically generate the polyomino. And by the way, the approach of just picking a square and then with equal probability picking one of the edges and just constructing it like this kind of as you go is actually not going to sample from the distribution we want to sample from, because I guess one of the reasons is because what you do early on has a huge impact on what happens later on in the generation. For example, the fact that I didn't put anything here means that now this is going to be this side heavy, right? And so I don't know. We were just told that this is not a viable approach. So instead, we were given this thing called the Metropolis-Hastings algorithm, and this is a special case of Markov chain methods, the Markov chain Monte Carlo method. And if you don't know what that means, don't worry about it. It's just a Metropolis-Hastings method involves starting with a polyomino. We just generate one. For example, you just generate a stick, right? This is you don't do anything random. You don't do any thinking. You just take a whole bunch of squares and stick them onto each other. Okay. Now the idea is that we now pick one of these squares with equal probability. We remove it, and then we stick it on somewhere else, like this. Okay, so we cut one of the squares off and we glue it on somewhere else, and now we have a new polyomino. And the idea is we keep doing this a whole bunch of times. So we're going to do it. Maybe we do it one more time, and we put this here, and we do it. We do it another time, and we put this here. And we're allowed to remove things that we've already moved once. We scribble this one out, maybe move it there, right? And you keep doing this a whole bunch of times, right? And the reason we want to do this is eventually we want to start analyzing stuff like holes. These 5 ominoes are kind of small. You can't have any holes in them. But the idea is the smallest polyomino you can have that has a hole in it is this big. 1, 2, 3, 4, 5, 6, 7, right? So this is technically a hole, right? We don't have a corner piece because corner pieces don't count. We need these 3 corner pieces because, remember, there has to be a path. They have to be strongly connected. They have to share a side. And sharing a side means that you should be able to draw a path from each from from starting at any node, going to every other node, and only passing through shared edges like this, right? Okay, so we talked about this like kind of high level how this is the Metropolis-Hastings algorithm. We talked high level about how this works. Okay. The problem is that what happens, remember I said you have to pick these with equal probability. What happens when, let's go back to our stick. What happens when we pick one of the middle pieces? Let's say we pick this one, okay? We scribble it out, and instead of putting it back where we found it, we put it over here. Okay, now we have two polyominoes, right? Because we have this polyomino, we have this domino, and then we have this triomino. And this is no good because these are, like, we want one polyomino. These are two polyominoes. How do we reconcile this? What we end up having to do is actually scribble this one out and put it back. Okay, so you notice one thing I did, and the one thing we have to do is actually every time we do a shuffle, we check to make sure the polyomino we have is still valid, right? To make sure that it's still strongly connected. Otherwise, it's no longer a polyomino, and we have to go back. Okay, so let's talk about kind of how we actually go out and do this. When we start, you know, when we do the sampling, like the specific steps that are involved, we have to do the shuffle, and then we have to do the check. And the shuffle involves three parts, right? Remember how I would take a piece off and put it on somewhere, right? I'm never going to take a piece off like this. Let's do another four-omino. I'm never going to take a piece off and then put it on here. Like, I'm actually, if you do that, you're just throwing. Like, you're not even trying, right? So what you do is instead you take the perimeter and then you figure out, okay, like it's valid for me to put a piece there. That's kind of what I was trying to get at earlier on. Like, okay, if I scribble this piece out and I find the perimeter, I can put it on anywhere where there is perimeter. So I can put a piece over here, right? So kind of for the shuffle, step one is to pluck a piece. Step two is to find the perimeter. And step three is to place a piece on the perimeter. Okay, and then the check step basically it asks, have we broken the polyomino? Okay, so we had a quick discussion of growth order. Let's talk about how fast each of these things are. And if it didn't make sense, like, it's like golf, lower is better. So plucking a piece happens in constant time, right? It doesn't matter how big your stack of papers is. If you just stick your hand inside the stack and pull a piece out, it's the same amount of time, right? It doesn't matter how long our polyomino is or how big it is. Taking a piece, same amount of time every time. Finding the perimeter. Okay, this one is a little bit more complicated. This takes order n, because to find the perimeter, we basically have to go to each one and say, do you have any air pieces around you? Yes, you do. Okay, let's add them to a set. Do you have any air pieces around you? You have this one and this one. Okay. Do you have any air pieces around you? You have this one and this one. Do you have any air pieces? You keep doing it, and since you have to ask for everybody if they have any air pieces around them to find the perimeter, it takes you just that long, right? And we have an optimization for this that's going to convert this into constant time, but then not constant memory space. So I'll explain, like, basically it means we have to store some things, and I'll explain how that optimization works later. And then we place the piece on the perimeter, and that takes order one, right? Because you're just putting it down somewhere. It doesn't matter how big your stack of papers is. Putting another paper on, same amount of time. And then checking. This one is kind of a bottleneck. This one also takes order n, best case scenario. Early implementation of this took order n squared, but then after we changed our data structure, we did some fine tuning, and we were able to get it down to order n. But our goal is to get this as close to order one or as low as possible. We want to see if we can get this sublinear. make it even faster than order n. Something maybe like square root n or cube root n or the logarithm of n or something like that. And we have something that we think is going, we have an approach that we think is going to get us cube root n. Because remember, the shuffle step is done a whole bunch of times and on very large polyominoes. So you don't want stuff like this inside. You don't want operations that take that many steps inside. You want operations that are just like one and done, that are very fast. Okay, let's talk about how we check the validity. We've talked about shuffling. Let's talk about how we check. So to check the validity of a polyomino, let's draw a couple of different polyominoes. We'll draw some that are valid, like this one. And then we'll draw some that are invalid. So this is valid. Let's draw another valid one. Let's draw like a ring. Or let's draw a broken ring, like this. So it's going to go right up to here, and then we break that ring, and then we do the same thing. Okay, and then we're going to separate them all into blocks so you can just kind of see what's happening. And there we go. We have our broken ring polyomino, and we have this one. These are both valid polyominoes. Let's look at an invalid polyomino. So maybe an invalid polyomino would be, like I showed you guys an example earlier, but this is an invalid polyomino, right? We could draw the same ring, actually, except it's not broken in one place, it's broken in two places. So let's do that. So it's got this, you know, we take it around, it has 3 in the middle, like that. There we go. Okay. So, oh, just kidding, I forgot to break it in one place. So we're going to pretend like this one's broken. Okay. Excellent. So we have these various polyominoes. So kind of the naive approach is to just take or actually in this case the only approach with the information I've given you so far, the only approach is to kind of start with one, like pick a piece at random, and then just go, or pick an arbitrary piece, it doesn't have to be at random. You just pick an arbitrary piece and you make sure that you can connect to all the pieces. You can make a trip to all the pieces from there. So for example, if I pick this one, can I make a trip? It doesn't have to be all in one trip. It's not like a put your pen down, you can't pick up the pen, but backtracking is allowed. So I make sure that I can reach every other piece through a strongly connected face from this piece. So I'm drawing little arrows here. So I go back here, so I backtrack, and I check to make sure that I can reach, all the other pieces from that piece, just like that. Okay, and this one is going to fail because I can do this, but I can't reach this one. So this one, not valid. This one, same story. We're gonna pick a piece. We're gonna go around, and okay, this is not valid because we can't reach these pieces, right? So now you've seen an examples of how we check validity, and this is actually how our latest implementation works, or at least the latest implementation in Python. Okay, now let's talk about optimizations. When we check, we're not like, this is not done in a vacuum. We do have a little bit of extra information. During the shuffle step, we know what we moved, right? It's like when you're playing chess. You can see it as like the current state of the board, or you can think about just what was the last move that was done, right? And if we just give it the current state of the board, it does a lot of thinking, but actually knowing the last move is actually relevant in this case. Knowing the last piece that we move to a different place lets us not necessarily have to check the whole thing, or check the whole thing with like just randomly trying to go and find, make sure that everything is connected to everything else. So when we remove a piece from a polyomino, let's remove a piece in a way that makes it not valid anymore. So we start with a valid polyomino always. We start with a valid polyomino like this, okay? But when we remove a piece, we might end up with an invalid polyomino like this. Okay, and we know that we moved this piece, and we know we moved this piece, and we know we moved it here. So how are we going to make that into how are we going to make that into something we can use to our benefit? For complex polyominoes, like where there's lots of neighbors and stuff like that. So maybe you have a polyomino that like looks like this. We're going to make this a little bit more involved. And, we have a polyomino that looks like this. And let's just do this. Let's give it that. right? So if I remove one of these pieces, the question is, do we break validity? So let's remove this piece at the end here, or actually let's remove this. Let's remove this piece, this one right here. Okay, so I'm going to scribble this one out. Okay, so how are we going to check if it's still valid? So what we could do is we could say, okay, by removing this piece, we definitely didn't screw with the rest of the structure. The rest of the structure should be in great shape, because if it was valid before, the rest of the structure should be valid now. But now by scribbling this one out, the question is, has removing this one caused any of its neighbors to no longer be connected? Because, in this case, removing this caused neighbors to no longer be connected. So the question that we're really trying to ask is, has removing this disconnected my neighbors completely? Like, am I the only connection that my neighbors have to each other? So what I do is I could start with this one and then kind of see if there's a path from this neighbor to the other neighbors. So these are the affected neighbors. There's this guy, and this guy. These are all the people that used to be strongly connected to the piece we just removed. So what we can do is we can see if they have an alternate path, like a detour to get to each other, and it turns out they do, and so it was okay to remove this one, and maybe we place it somewhere else that's like irrelevant, like over here, right? So now we know that this is actually a valid polyform based on the thing we just removed. There are still paths to all the neighbors. The three affected neighbors still have a connection to each other. Okay, let's go. So this is that. Now let's go to kind of how we can make this faster. Or no, let's talk about why this is slow first. Let's pretend. Let's go to our kind of our latest state, the shuffle we just did. Right, we did all this. I'm trying to copy the piece exactly. So we removed this piece, and we're going to do this. Okay, and put dots in all of these, and then put this guy. Okay, now remember this guy, this is not strongly connected to that because they're only sharing a corner. Okay, now let's pretend we removed this piece. Okay, and now we start on this piece to see if it's still connected to that. So what are my neighbors? This is one of my neighbors. This is one of my neighbors. Let's start with this neighbor. So the optimization would try to go in the direction of my other neighbor, right? Instead of trying to go in some really long winded way, I just want to see if this can get there. And so I'm going to try to go up. I can't because this was just removed. Okay, fine. I'm gonna have to try to go a different way. So I'm gonna go left. Okay, that didn't help. Dead end. We're gonna try to go right. Okay, we can go right. We can go right. Oh, finally a way to go up. Oh, that didn't work. Dead end. Okay, fine. We'll go right. All right. This is going to take the same amount of time as the unoptimized algorithm, the one that we were talking about over here, right? Where you just kind of just pick a direction, just go in it, and then if that doesn't work, pick another direction, and at every decision point, pick a different direction, right? So this is going to take about the size of the polyomino at most, right? Maybe half the size of the polyomino, maybe quarter the size of the polyomino, but we're still going through a whole bunch of pieces to see if there's some path. And for very, 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 very large polyforms, this can take forever, right? Or not literally forever, but quite some time. And especially if we're trying to do shuffles and get, because this is just one step in the process. If it takes that long, it's going to be a problem. Okay, so this is an optimization in some cases, but not in all cases. In fact, in many, many, many cases, especially early on, for when you start out with a stick, more often than not, you're going to be doing this. And so this only helps sometimes. And it's good, but it only helps sometimes. It's better, but you're still going to end up, you're going to see a good performance increase, but not huge. It's not going to be ridiculous. You're still going to have something that looks kind of ON, because this case happens more often than that case. So this is rare. In the off chance that you end up actually doing a good thing, it's going to look like order n. It's not going to be super stable, but it's going to look like order n. We want something that's even faster than this, and we've been thinking about it for a while. And so here's here's what I came up with last night. Okay, so one thing that we do. Let me actually explain how we did this. I have to talk about, before I can talk about how we sped up check validity, or how we're planning on speeding up check validity, I have to explain how we can find the perimeter in O1 instead of ON. And the way we do that is by storing the perimeter with the polyform. So one way to think about that is instead of like we do all this perimeter calculation, we sit here and we go through every single piece, you know, let's just draw a 5 omino really quick. We go through every single piece and we see what its perimeter looks like, right? Just like that. Now, if I remove a piece, I don't actually have to go, I shouldn't have to go back and recompute the entire perimeter. Like this, all of this perimeter should have been left unchanged by removing this piece. The only perimeter that should have been changed is the perimeter bits that were directly connected to it, like these 3, right? And then itself. And so by removing this piece, we haven't substantially changed the perimeter. We should be able to just use the last computation for the perimeter and then modify kind of what we remember to be our perimeter. So the way we do that is now that we've removed this piece, we're just going to draw it again like this, and you know, now this is our perimeter, and I actually don't have to go through and think about these. I just kind of modify our storage of the perimeter here, right? We remove this piece, these 3 bits disappear, these 2 things of perimeter, and then we have a piece over here that's now become a perimeter piece, right? You're basically guaranteed when you remove a piece that piece becomes a perimeter piece. Sick. Okay, so that's how we do the keep track of the perimeter in O1, just by remembering what the last perimeter was and then modifying it. Okay, so that explains this. So now what we now have is we have O1, O1, O1. The shuffle process is blazing fast, right? The check process is still stuck at ON. How can we speed this one up? Okay, now I'm going to introduce the cut algorithm. Kind of the slowest, the worst case currently for, remember I said for our polyform check validity is something that looks like this. In fact, when we start shuffling, we actually start with our worst case. This is the thing we initialize to. We start on the wrong foot, and the polyomino we end up shuffling will look like this for a long time. It'll take a lot of shuffles to start making this into something that looks more clumped around, where our algorithm like this is more likely to be in this state than in this state, right? More likely to have something valid than something that's invalid. And so the worst case is basically that we cut this one out, and when we do that arbitrary picking of something to start at, we pick this one, and then we have to go through all the way through here. Because remember, we have to go all the way through here because we have no idea if there's some really whack shit like this happening that connects, you know, that connects this. We actually don't know if this is true or whether something like this exists. So we actually do have to go through and explore all the way down like this, all the way down until we hit this. And let's pretend this one never existed. This was just for demonstration purposes. But like we're gonna have to go all the way down this whole thing, all the way until we reach the end. We say, okay, now there's no hope for us to connect this piece to this piece that we just separated, right? There's no way to get to the neighbors. So what I've decided is actually we're asking the wrong question, right? Or there's a question that we can ask that gives us the same answer, or that answers the same question, but takes advantage of other information. So remember how we know that the polyomino we started with is a valid polyomino, right? If it's broken because of a removal that happened in only one place. So let's go look at that, right? So if it's broken because of a removal that happened in just one place. So in the case where we remove, let's pretend I just removed this piece. I just removed this piece. It's no longer here, right? And let's draw ourselves our perimeter. Our perimeter looks like this, right? And this is going to be the perimeter before we remove the piece. So you can imagine that there's still a piece there. Okay, there's still a piece here. Imagine that. And this is what the perimeter of that thing looked like. And now we've removed this piece. Now we maybe put it somewhere else. Who knows? The question of is this valid is actually now, has this piece broken the validity? And the way we can answer that is, can we draw a path connecting the outer perimeter to itself through the piece we just removed? And I say outer perimeter because if you're like, you really know this stuff and you're like, oh, what if there's a hole, right? Okay, so that doesn't count. Even though a hole is for our definition of perimeter, does count because a hole is a valid place to place a piece. In this case, we were able to connect the outer perimeter to itself. So what that actually entails is the perimeter is still like the outer perimeter is just a way of drawing a circle around these things. So if I was able to connect the outer perimeter to itself, that means I actually now have two pieces. And this is a lot faster because in this case, it only took me 3 steps, or actually 1 step. I had to check up, down, right? And so this, for stick pieces specifically for stick pieces, it's going to run in constant time, right? When you start to see this thing degrade is when you end up with something more like a ball. And by degrade, I don't mean that it's going to degrade into like, oh, now it's going to take n to the n or anything ridiculous like that. By degrade, it's still going to be sublinear. It's not going to have to go and explore the whole thing. It's going to take something closer to cube root of n, right? And that's still a lot better than n. Like this is, kind of the graph of n looks like this, and then cube root of n is going to look like this, or not actually that. It's not going to go down, but like it's going to look like this. And so in practice, I think the complexity is going to look something like this. Initially, it's going to be constant time, because while you're still in a stick state, and then while it's still stick-like, it's gonna slowly increase, right? Very, very slowly, because it's still mostly straight. And then as it starts to ball up after a ton of these, it's going to start growing like this. And that's opposed to our current growth, which looks like this, right? And so for big polyforms, we want to be in this case, not in this case. And that's kind of the where I'm at right now. For the 3D case, things get a little bit more dicey, but honestly not that much more dicey. Like there is it took me, after I came up with the 2D case kind of like cutting algorithm, the 3D case really felt like the 3D case took some thinking to get to, and it took maybe a few minutes to go from the 2D case to the 3D case. But the 3D case, there are some other concerns, like making sure that it's actually correct for the 3D case, that it is valid to take this thing that I came for the 2D case and take it to the 3D case and have it still work. I am interested, like we're interested in 3D polyforms. There is current research done by Dr. Roldan, who's been one of the mentors for this project, for the 2D case. And I wonder if an algorithm like this might speed up the 2D case. Now, when I spoke to Dr. Roldan, they said that the check validity step is the longest step. And actually, that's still true even with our optimization, right? It's still going to be a very quick step, but it's still going to be longer than all of our constant time things, right? So this check is now going to be something that looks like, cube root of n, right? Is the very rough growth order. It's still going to take longer. And so this is a pain point in general for this research. But it is something that we've made some progress in, and hopefully after I finish the 3D case, or maybe even before I start the 3D case, I'll write code for the 2D case and see if we can generate something something similar to what Dr. Roldan generated. Dr. Roldan generated some really large polyominoes, and I wonder if we could maybe get bigger or get the similar sizes quicker with this algorithm. Or it's possible that Dr. Roldan has a very optimized version of this algorithm that actually, turns out everything I'm saying here doesn't apply, because Dr. Roldan's algorithm already covers this. I think we'd be able to see bigger polyominoes in 2 dimensions and bigger polyominoes in 3 dimensions with this algorithm. And if anyone else has an even faster algorithm, I would really appreciate it. Please let us know. We will credit you appropriately if you can think of something that runs quicker than this, or if you can find a way to improve this. Right. This is just for the 2D case. For the 3D case, where we're really concerned about optimization. But anyways, thank you for spending the last half hour with me. If you guys have any questions, I'm happy to answer them.